Okay, so welcome to the morning session, and happy to have Tomoyuki Yamakami here, who's one of the pioneers of type 2 complexity theory, and so let's just welcome him and enjoy his talk.
Thank you very much for the organizers to inviting me to the meeting here. Well, the title is Type 2 Computability, and in some connection to the generic oracles, and some recent topic about linear space and hypothesis. Roughly, I'll follow the this schedule here. So I start with Type 2 Computability. This is a kind of an old result, and some connection to the generic oracles here, the relationships. And then I move on to the different topic that covers the last 4 chapters. Okay, so this is an abstract that I send out to you. So I just simply skip this one. So this talk is based on the 9 papers of mine. So those are the old results in the 1990s, starting with 1992. 95, 96, 97. That covers the generic oracles and type 2 computabilities. And then the second part of the talk covers the satisfiability problem, and well, particularly the important thing is the reductions. And then I just put some restriction on the reductions in space, not time. So that's very different from the talks we have heard during this seminar. And those are actually the new ones. So this is Impress. So you can get the Impress version of online. Okay, so this lecture slides are actually based on my lectures. So I have 15-week lecture, and then all the slides are actually posted on the web page. So if you are interested, maybe take a look at the slides. Everything is written in English. So, well, but then I convey all the lecture to Japanese in Japanese. Okay, anyway. So you can actually access the homepage by just use Google search. Okay, so let's start. Let's get started. Type 2 computability. So this is just a brief history up to the 1995 when I just came into this field, right? We start with Constable and Melhorn. They initiated the functional approach to the polynomial time computability in a little bit higher order. And then Townsend reformulated the notion here, and then formalized the type 2 functionals. So, and then Bass considers the polynomial time computability of type 2 functionals. Is that right? Yes. Okay, and then Cole, he introduced similar concept using operators, so slightly different aspect. And then I did some the extension of the Townsend formalism, and then talk about it in the type 2 computability and functionals. So I start with the basic model of the Turing machines, right? Turing machine is everybody knows this kind of structure, and the program actually can dictate how to what the next step could be, right? So if you see it, then you have to read the symbol and the cell, and then the instruction says P to be Q, and the sigma has to be rewritten by tau, and then you have to move to the right. Then it just goes like this one here, right? So basically it is not sticking to that model, and then I just add an oracle. So an oracle, to access the oracle, the machine has to have the extra tape called the query tape. This is usually in write-only tape. And the oracle is an external information, and give the extra information to the machine to enhance the computability. So this is actually the schematic picture of the machinery here. So we have a read-only input tape, and then we have a read-write, rewritable work tape, and we have the query tape. So this is write-only. So whenever the machine writes any string here, and machine enters in the query state, then whole entire information is transmitted to an oracle. An oracle make a decision whether answering yes or no, right? Depending on the string is actually belonging to the set or not, or language, in other words. Okay, so the oracle computation goes like this one here, right? Then the machine starts with an input X, and then write a query word, like a Z1, and then enter then a query state called the Q query, and Z1 is actually transmitted into the oracle, and the oracle make a decision whether Z1 is inside the set B or outside of the B, right? So the answer is yes or no. This is actually directly changing, well, the answer is actually made by directly changing the internal state of the machine. And the query is adaptive, so the next query must be depending on the answer of the oracle, and so on. And eventually the machine output m of x, and that has to be correctly computing a of x, right? This is the characteristic function of the set A. So this is the basic model, right? And based on this oracle mechanism, we can actually define the polynomial hierarchy or polynomial time hierarchy, starting with P and NP and co-NP and so on, right? So we are going to use this one later on, so just to keep in mind. Okay, so now I want to move on to the functionals. So now, instead of taking the set oracle, so we are actually considering the function oracle. So we will use the following notation. So basically, this comes from the Townsend notation here. So omega represents the set of natural numbers. That means non-negative integers, and omega is the set of the total functions from omega to omega. So the function on natural numbers. And k comma L omega, that means the first k is, suppose this is actually example here. 3 comma 2 omega means that we have type 1, 3 inputs, and type 2, type 2, 2 inputs. Those are functions on natural numbers. So I just sticking to this notation here. So m corresponds to the first k natural numbers, and then alpha corresponds to the L functions. Okay, the partial function is the subset. The domain of the functional is the actually subset of this KL omega. And if I said just functional, that means the total functional. Then that's the domain is exactly defined on all inputs in KL omega. The relation is the outcome of the function is just 0, 1, or just think about this is a predicate or whatever. Okay? All right. So the model, so I have to change the original model. The models that I mentioned a little bit. So now the oracle has to be a function, right? So instead of the oracle answering yes or no, the oracle answers or returns the strings. Well, in a binary case, it's just a number or whatever. So the machine wants to make a query, then he actually to write down the query word on query tape, and then the machine enters query state. Then, so this happens automatically, right? Whenever the query word is sent to the functional oracle, then the query tape becomes empty automatically, and the tape head is jump back to the original state, starting state. So this also happens. This happens automatically too. And the oracle, the function oracle f, returns an f of z. Directly write down everything onto the query tape, like this one here. So the machine writes the query word on query tape. So the head actually stays here, right? And then enter the query state. So automatically the query tape becomes blank, and then this head is returned to the start cell. Then function oracle write down the whole answer onto this tape. So this happens just a single step. So I'm not counting then how many steps or how much time then the function oracle write down the answer to the tape. Okay. Now then the machine has to start from here to start reading the whole entire information, right? And that's also counted as the steps, the number of steps. So the partial function is called the polynomial time computable if the function oracle Turing machine compute this function f in polynomial time. So important thing is the function oracle may possibly return a very long, extremely long answer into this machine, but the machine needs an extremely long time to read the whole entire stuff. But the machine, it has the restriction on time, so the machine may not read entire outcome of this function, right? So that's the key issue. So just to keep in mind this, the restriction here. The relation is polynomial and computable if the characteristic function of this relation is polynomial time computable. That's natural. Okay, so now we introduce the function classes. The first one is the class of polynomial time computable total functionals, PTF, the polynomial time functionals, PTF. So this is actually the starting point of this whole entire things, right? Now I can add an extra oracle, or this is actually set, right? The PTF of A. So this is the polynomial time computable functionals relative to this particular oracle. So now I have the relativization of the functions. And we can actually take them the set of languages, right? Just taking the union of all possible PTF of A is taken from C. Now you remember the polynomial hierarchy, right? So we just simply follow the same kind of definition, starting with the functions. So we have a superscript and a subscript. The superscript is 0, p all over the definition, so I just simply skip it. Okay. So delta 0, sigma 0, pi 0s, and all are exactly the same as the class of polynomial time computable relations. So that means the functionals outputting is either 0 or 1. Right? Now, the sigma k plus 1 is defined by this particular relation. The R comes from the pi sub k. So the subscript k plus 1 here is a k. So the recursive definition here. And f is the polynomial time computable functionals. So the existential quantifier is actually, well, the x ranges over natural numbers. And the number is bounded by the value of f. So this is polynomial time computable. And well, the dual notion is actually pi sub k plus 1. That is defined by using the universal quantifier instead of an existential quantifier. Right. So as you see, the base machine runs in polynomial time. So the outcome of this machine, or the outcome of the polynomial time computable functionals, is bounded by polynomial. So the size doesn't grow bigger, right? So this is the polynomial. Well, the size is polynomial. So the natural numbers, to do the polynomial. So that's the outcome of this functionals. Okay, so we only considering the exponential number of possible candidates here and here too. Okay, So we can also expand this in a PTF using the oracle taken from the sigma sub k here, the definition, right? And that goes to the box or scale sub k plus 1. The delta k plus 1 is the actual relation part of this function. So that's the whole definition here. According to this definition, the Townsend actually proved in a very interesting things. All hierarchy, whole entire hierarchy is infinite, so that then we can separate in each level. And also the box sub n and box sub n plus 1 is different too, right? So now what I did is that I introduced kind of an intermediate level, defining, well, do you remember the delta k plus 1 is defined by the the characteristic function, characteristic functional of R is computable in polynomial time relative to the oracle sigma sub k, right? Now, instead of taking this one, I just take k minus 1 and adding the classical type of object to sigma sub k from the standard polynomial hierarchy, right? Now you see the difference here, right? So that I just describe this whole entire the class as delta k plus 1 super np, because then I'm using the np based class. Right? So an interesting thing is this characterize the collapse of the some level of the polynomial hierarchies, the standard polynomial hierarchy. For example, the delta n and the sigma n both coincide if and only if delta np n plus 1, this one here, right? So that's collapsed to n. And the similar thing happens here, right? This is the sigma level and the pi level class. And that is actually characterized by delta n plus 1 is included in the intersection of the sigma n intersect pi n. Yeah, it's kind of nice, right? So we have a bridge between the classical, standard, the polynomial hierarchy, and the polynomial hierarchy of the higher functions.
So is the problem that you mentioned of this extremely long answers
It's
not
chopped
a
off.
problem here?
Yeah, that's right, that's right. So I'm just using that definition. Okay, so now move on to the generic oracle. I just try to explain what generic oracle is, and then I'll give it some idea on how to relate this notion to the previous type 2 computability. The generic oracle, well, definition is slightly complex, so just if you have any questions, just simply ask me. Blum and Pagliazzo, they introduced a notion called the generic oracles, and it's a kind of oracle, but the particular kind of oracle. So I'm going to use the characteristic function of the language using chi sub a. Right? Now the condition is the partial function from the binary string to the Boolean value. But the important thing is the domain size is always finite. Okay, so it's a finite function. So this is a finite function, so we can identify this condition with the string. So the string and the condition are pretty much the same thing in the following argument. Okay, so the condition tau extends sigma. So we use this notation. The tau extends sigma. Sigma is extended by tau or whatever. So the domain is expanded here. The domain of sigma is included in domain of tau, and within this smaller domain, the sigma and tau coincide. Okay, but the expanded part, well, we don't know. Okay? So the set A extends sigma. Sigma is a condition, right? We use the similar notation here. A extends sigma. If the characteristic function of A extends sigma, well, in other words, here, any x in domain of sigma, the value coincides. Okay. Well, because in A, the characteristic function of A is a total function, so it's slightly different from here. Right? Oh, I just give you example, simple example here. So those are the strings, the binary strings, and suppose we have sigma and tau, those are conditions, and this is the characteristic function of set A. Suppose A contains those strings, right? Now, here the blue circle said sigma maybe is not defined on 1, 0, but tau is defined, right? And also the other part are actually exactly the same. So there's no contradiction between the sigma and tau, because here is the tau, sigma is, the value of the sigma is not defined, but the tau is, so there's no confusion, no contradiction, right? And here, the value, those values are exactly the same, right? So that's the idea of the extension. Simply we will get like this one here. It's the domain, well, the domain of tau expands the domain of the sigma, and whatever thing of the domain, well, the input is defined, the value are exactly the same, right? And for A, so A contains this one here. So now we have exactly the same value here, right? So there is no contradiction. So this is the extension. So this is just a simple example. Now, so now we actually try to define the generic oracle, right? So we use the standard oracle Turing machine. And so the M is the oracle Turing machine, and the sigma is the condition. Now, you remember that the sigma is the finite function. So we try to use an oracle. Then we use this oracle, right? The oracle is the language or set that contains an X, and sigma actually maps X to 1, right? But there's a catch here. So the machine, whenever the machine make a query, whose query word belongs to domain of sigma, then the oracle correctly answers to the machine. But if the machine asks a query whose string is not inside the domain of sigma, that means that outside of the scope of this condition, then the answer is undefined. Okay? So that then the machine has to always ask the query inside this domain. Otherwise, the answer doesn't make much sense. Yes?
But there will still be an answer, or does the when
they say some kind of question mark or something.
This may be a subtle point. So you could also conceivably say that when making an oral query to something which is not in domain sigma, the query will not answer at all, as opposed to answer arbitrarily. Does that make a difference in your setting?
Oh, I see. Oh, yeah, that's right. So I just make this clear. Okay. Well, undefined means that maybe you are running a machine, right? So machine receives the answer, say question mark or something. So this, you clearly know that your answer, your query is.
But that means you get the information that is not in the domain, and that does it sound right to be?
Yeah, but then you want to get the information from that sigma, right?
Okay.
But then your answer is just a question mark, so it doesn't make much sense, right? Yes. Okay. So this is the setting here. All right. So the set of condition. The set of condition is called dense. That means, for any sigma, right? This is the condition. We can always find tau inside the S that extends sigma. So S contains enough information, enough condition that covers all other sigma in the sense of the extension. So you can always find it an extended version here inside S. So that means in that case S is called a dense. And a set S, set A is called to meet a set of conditions. If there exists a condition sigma in S that is extended by A. So the A always extends something, and that something is inside S. Okay. And set S is called an arithmetical. That is, an S is exactly defined in the first order arithmetic. It's just simply easy to define that in some arithmetical way. Okay. So the set G, so this is just a standard set, right? G is called generic. If G meets every dense arithmetic set of conditions, no matter what the dense arithmetic set of condition, you can always, G always meet this set. So this is the definition of the generic arc. So you might see that the generic arc is not unique, right? There is the infinitely many possible choice. Okay. So I introduced the well, some of you may already know the class called the UP. So this is actually a restricted version of NP. The only difference between it and UP and NP is the number of the accepting path. Right? When X is in L, that means in a positive instance, then we only have one accepting path. Well, in the NP case, maybe we have made more. Right? In the negative instance, there is no accepting path. So the U in UP stands for the unique or unambiguous. Okay, and also we can actually add the relativization. So this is the entire polynomial hierarchy. So we have the P and NP, right? And the UP comes in between P and NP. And we don't know whether the P and the UP and the UP and NP are different. So basically nothing is known among those classes, whether they are actually collapsing or actually coinciding. Okay. So now I'm going to explain about the result about the generic oracles. And here, the single generic, well, the beauty of the generic oracle is the following. For example, if the one generic oracle satisfies this condition, like an NP class to P, then for all other generic oracle H, the same thing happens, right? So you only prove the separation or equality for one single generic oracle. That's enough. So that all other generic oracles follow the same property. Right? So this is the beauty of the generic oracles. And
could you
yes.
repeat the
Okay.
definition of generic oracle for me?
The definition of the generic oracle or the property of the generic oracle?
The definition.
Definition, okay.
This is question. Just I want to get more.
This one here. Okay. The generic oracle is for any dense arithmetic set of conditions, like something like this, right? And then this particular oracle always meet this set of conditions. Meet means you can always find element inside S that is extended by G. Yeah, well, I know the definition is slightly complex somehow.
Okay.
So if this 8 subset sigma
Oh, sorry.
star is meant, you talk about the characteristic function of A in the sense what we did earlier in the second
Here?
area.
Oh,
of this.
okay.
Yeah, it's considered as a
Yeah, that's right. So you can think about the characteristic function of A. Yes, that extends the sigma.
and the domains are actually coded. Yes.
Yes, so this is actually finite function.
And first order arithmetic means with respect to natural numbers,
Yeah, that's right. That's right.
identified with their binary representations as sigma star.
Yes, sigma. Yeah. Well. Okay. So you can always translate the string into the numbers. Numbers is a string, so not much difference. The important thing is just you can actually define the precisely the set in terms of some arithmetic formulas, first order formula. Okay, and then I move on here. So Plum and Impanriato proved that for any generic oracle, do you remember that one single generic oracle satisfies some condition, the whole entire generic oracle satisfies the same one, right? For most of the the property. So at least one generic oracle satisfies this condition. That means the generic oracle separate NP from P. Okay, but for UP case, slightly the situation is different. Assuming NP collapses to P, then we have a generic oracle that collapses UP down to P, and also NP intersect co-NP down to P. But we need assumption. Right? Now it's subtle somehow, NP and UP, definition is similar somehow, but the situation is quite different.
But why do you call this claim? So it's proof. It sounds like a conjecture.
Yeah, it's just kind of part of the long lecture, so I just put in the proposition and so on.
Okay.
Yeah, that's just the theorem somehow.
The theorem.
Sorry, I have another question.
Sure.
So there were recently some results about random oracles. The polynomial hierarchy is strict relative to random oracle with probability 1. So are random oracles generic? What is the relation between generic?
Well, basically, it's a very totally different concept. Oh, yes.
Actually, don't ask me precisely. Yeah, there's a genericity condition. You can get random oracles as generics.
Say it again.
Yeah, there is a genericity. There's a kind of genericity condition where you can get random oracles as generics. So yeah, there's a funny notion, not this one, that we can get random oracles under this.
Well, there are several notions, concerning about the genericity. This is just the very early one I told you about. Yes. So now, so we are going to talk about an extension of their result. And what about the higher level of the polynomial hierarchy? Do we have the same result or a different kind of result? Right? Extension could be possible. So this is the result here. So first I have to expand UP to U delta K, right? Delta 1 is exactly the same as P, right? So now we actually move up to delta 2, 3, 4, 5, and so on, right? So the definition is very simple. U delta 1 is P. Oops, sorry. It should be 0. Sorry. And U delta 1 is UP. And U delta K plus 1 is the UP relative to oracle from the sigma K. So that's the number, the subscript is increasing here. Okay. So that's actually nicely sit between delta K and sigma K intersect pi K. Okay. So the result we'll get, this is actually the old paper. If K is at least 2, right? Well, the first case, when the K is equal to 1, the Plum and Impanriato will have a result, right? Now we actually looking at the higher level in the polynomial hierarchy. Well, U delta K intersect pi K is different from delta K for any generic order G. So as a corollary, we will get the sigma K and the pi K, the intersection of the sigma K and pi K is different from delta K, without any assumption. Right? So that is very different from the first level. So you see if the levels goes up higher, then the situation is completely different. Is that okay?
So,
Oops.
just
Sorry.
So there, obviously you didn't really separate the polynomial time hierarchy, so there's no condition under which you would get, like Plum and Piazza for K equal 1 got under the assumption
That's
that
right,
they're equal
that's
for
right.
P equals NP, but here there's no under.
That's right. Okay, the open question might be so what about the U delta K intersect co-U delta K, right? Much smaller, very close to delta K. So I don't know the separation between those two classes. Maybe you need some more technique somehow, right? and some separation class of the complexity classes relative to generic groups. So we have to find more separations. That would be a nice thing. And then, so this notion is somewhat related to the type 2 computability we have discussed before, right? So this subject will be discussed in the next session, next chapter. Okay, so this is the relationship between type 2 computability and the generic law. So this is more important and more, important for all of us, right? Okay, so now we have to think about the relativization and the type 2. Okay, so we start with the type 1 complexity classes. Well, just a P, NP, and BPP, and you name it, right? So that is C. And then if I just write double bar on top of C, that is a natural type 2 counterpart. So if this is the C is equal to P, then the P double bar is the natural type 2 counterpart. And they have to have the same resource bounds, and the same, naturally they have a relativization. Okay, so that's a kind of assumption. And those classes actually satisfy this condition. So you can actually imagine those complexity classes actually taken as C. Okay, well, because we are only sticking to those kind of things, not talking about anything else. Then just think about those things. Okay. Now, so suppose R is a type 2 relation, and then we take oracle, just standard set oracle, right? And then we write down the R of A as just fixing this element, right? And the X is the variable. Okay. So just the notation here. So we collect those things, just fixing A, right? And collecting all possible R taken from C. And then I prefer to write down like C double bar of A. Okay, so we fix the functional or set part. And then just think about it, this is the kind of the standard classical set. Oh, this is the class. All right. So using those notations, there are two separate constants: regularity, the regular or irregular. Say now we have a type 1 object C, and this is the relativized version of C, right? And now we have a C double bar, that is the type 2 counterpart of C, and fixed oracle A. Right? Now, both concepts are exactly the same for all possible fixed A. So in that case, this complexity class C is called the regular. So what kind of the regular set? The P and P. Those are regular complexity classes. All other complexity classes are regular? Well, actually not. So there are irregular ones. For example, here, NP intersect co-NP, like a BPP. Those are irregular complexity classes because if you take the proper oracles and B, right, we can actually separate two constants. So this one, well, this is the standard classical complexity classes. This is actually induced from type 2 counterpart, right? And also BPP. Well, the main reason why we have the difference between the two complexity classes here is that well, it's just a kind of a uniform, or say, well, here. So when you define this complexity class, and so you have for any the functional input and the type 1 object, so you can always define the computation here. But then here it's not like that. There is a NP machine here, and this is a co-NP machine here, and then they run the both machine, and then we always consider the something comes from the element of the input that actually that matches the both results, right? So sometimes NP machine or co-NP machine does not match, right? But sometimes they do. So it's not the kind of a uniformly defined. This notion is not uniformly defined in some sense. Okay.
So is that connected, I mean, it is connected to Papa Demetrio would call those semantic classes. as
Yeah,
opposed to
that's right.
syntactic classes.
Yes. And also, this is also the same. Well, because we have to have the probabilistic computation somehow, right? All right. So the close relation, I'm going to explain about the relationship between the generic OAK and type 2 computability. Right? For generic OAK, C to the G is included by the D to the G. So this is the standard complexity class relationship. And this is the counterpart, type 2 counterpart. That is actually the same. For generic OAK, so if you use the generic OAK, then the situation is completely different. For example, so this is true for any OAK. So even though we restrict our interest into the generic OAK, but still the equation or equality holds, right? But for co-NP intersect co-NP and the BPP, right? Standard OAK setting, we have the two OAKs that separate the two counterparts. But if you restrict our interest within generic OAK, they exactly characterize two concepts. So now this is the power of the generic OAK, or generic OAK actually brings the two concepts together. So this is the use of the nice usefulness of the generic OAK, right? Even though the situation like this happens. Okay. Oh, so we have lots of problems about the generic OAKs, right? Try to find more the complex classes and so on, and also think about them higher order, like a type 3, type 4. What happens? Lots of theoreticians are interested in the type 1 object, like polynomial hierarchy, cross of the polynomial hierarchy. So type 3 computability have some information to the collapse of the standard polynomial hierarchy. That would be great, right? Okay.
So this is something I've always wondered. So the definition of generic meeting every dense arithmetical set. So arithmetic, if you weaken the kind of, you could weaken it by having not sets that are arithmetical, but somehow more weakly definable.
Yeah, that could be possible, yes.
And will that,
Probably.
do you have any intuition if that's going to change? Will the results still hold in that case?
I don't think so. Yeah, you need some kind of the power to kind of bring this one into here.
But it's just to be able to do coding or something, or?
Yeah, it's sort of yes.
Yeah.
But I mean, you shouldn't really need full arithmetic definability, right?
For every doubt, yes.
For every concrete result, sort of, you should be able to sort of see how many quantifiers you need, and then sort of maybe 2 generic, 3 generic, whatever should work.
Okay, so I'll move on to the second part of the talk. This is more recent work. So I'm going to talk about parameterize NL. NL stands for the non-deterministic log space problems. And I'm going to use the similar machinery, but instead of accessing the input tape by just moving the head. Instead of that, I'm using the index tape. So that we write down the address, and then the head actually jump into the address that is described by index tape, right, in a single step. So this is the random access model. And to measure the low space bounded complexity classes, then we have to have the rewritable work tape. The input tape is untouched. Right? We are not going to change anything. Okay. So this is how to operate the machine, but I just simply skip this one So NL, non-deterministic large space. So this is defined by the non-deterministic Turing machine with an index X, the random access model. And when X is in L, we have the accepting computation path, right? And M uses the logarithmic space, or log space, in terms of the size of the input. Well, I'm going to change it later on because it's parameterized. So now the ML sit between an L and P, but we don't know whether the P and L are equal or different. Right? And the completely different from the NP, NL is closed under complementation. So NL equals co-NL. So the NP and the co-NP, we don't know whether they're equal or different. Right? So that is very different. So the approach to the low space-bounded complexity class is very different from the time-bounded setting. Well, in a p-space case, we have the same thing. Right? Okay, so this is the one example of the NN complete problem. Okay, so 3 SAT is NP complete, but if you use an N2 SAT, then that is NL complete. So the problem is something like this one. For instance, the Boolean formula in 2CNA form, right? 2 conjunctive normal form. And the question is, well, this is a yes/no question. Is phi satisfiable? So yes or no, right? There, for example, here, right? We have the 2 literals, and this is actually in this 2 SAT is NL complete, proven a long time ago in 1975. But that is a really long time. And we can actually weaken the 2 SAT slightly using subscript K. The K stands for the restriction, the following restriction. So we are talking about a 2 SAT formula, but each variable that appearing in the given formula appears at most K times, just ignoring the negation symbols. For example, here, the x2, the variable x2 appeared 3 times. But then here is we have the negation symbol, but simply forgetting about the negation symbol, just the literals. And as the literals, x2 appeared 3 times, at most 3 times. So that is the case of k equals 3, right? And 2 SAT sub k, if the k is at least 3, is still NL complete, right? But we don't know whether this contains NL. So that is actually essentially the question of L equals NL. Right? And another example is DST comp. So directed ST connectivity problem. So this problem is also called the graph connectivity problem and so on. Right? There are several different names. The directed graph is given, and also the 2 vertices are specified, something like S and T here. The question is whether we have a path from starting point to the ending point. Right? Yes, no question. So this problem is also NL complete, proven by Jones, 1975, so a long time. Now we can restrict this problem slightly. So K DST con, that means in every vertex or node, they have a degree at most K. In this case, it's 5. Right? So the graph is much simpler in some sense. But this problem, when K is at most, less than or equal to 3, K DST con is still NL complete. Well, the important thing is the directedness of the graph. If you just forget about directedness, if you just take an undirected graph and think about it in the same question, so this problem belongs to L. Right? It's just a subtle, but the L and NL might be characterized by just looking at the shape of the graph. Right? Directed graph, undirected. That's the huge difference. Okay. All right. Okay. So now I just give you the algorithmic result here. So supposing the input is the directed graph, with the n vertices and m edges. Right? Now we have parameters here. Right? And Barnes and Boston, Russo, and Scheibler, they gave the deterministic algorithm that solved the DST cone with m edges, n vertices in n plus n time using n here n to the 1 minus c over square root log n space. So this is smaller than n, slightly small. But you know that when n goes bigger, right, is close to n. Right? So, but still there is the open question is, we can actually improve this space bound something like n to the epsilon. Epsilon is a constant, smaller than 1. Because this is not this is not constant, right? And well, this is just additional term, polylog n plus n. So this is actually not really necessary. So if you just use a little bit bigger epsilon. Okay, so this is actually an open problem. Still, well, this algorithm is presented in 1998, so still, this is open. Right? Okay, now we see the parameters are important. So I call it the size parameter. Size parameter is the function that actually specifies the size. Well, then a simple example is here, right? If x is an input, then binary string length of the binary string. Right? That is actually one of the parameter or size parameter. But we can take something else, like the number of different variables in a formula, or number of the clauses, for example, right? And in a graph, it's the number of the vertices, number of the edges. Those are the possible parameters, size parameters. Right? Now you see that if this is actually taken as a basis, or this is taken as a basis, situation might be different, right? Well, you might be surprised, actually. But anyway, so this actually illustrates the difference between the two size parameters. This is the number of the vertices, number of the edges. Well, if you look at the very sparse graph or a very dense graph, right? The number of the vertices is upper bounded by the number of the edges in the linear factor, right? But here, the number of the edges is bounded by the square of the number of the vertices. So then we have a square here, right? If you're actually going down, well, polynomial time level or polynomial space, it's a polynomial, so it doesn't matter then the square, you can take a square or not. But if you really goes down, then these make a huge difference. Right? Okay. So, in Pariato, Tomoyuki Yamakami, they introduced the notion, they discussed K-SAT, like 3-SAT, 4-SAT, 5-SAT, right? Those are NP complete problem and the search version, right? Using the parameter, number of the variable, number of the clauses, right? So this is actually the way. Well, this whole entire parameterized setting is actually taken from their work. So the parameterized decision problem is actually pair, the standard set and size parameter. Okay. Well, usually we'll take a log space computable size parameters because the size parameter could be not computable, right? In general. So the instance is x with the size parameter, and this is actually the yes/no question, decision problem, whether x belongs to A or not. Now I'm going to sublinear space computability and also the reduction. So reduction part is the most important, interesting thing. So we use a deterministic Turing machine and index state and readable input, read-only input tape and rewritable word tape. The situation is the same as before, right? Now we are interested in the polynomial time algorithm, but we have a very restricted space usage. Okay. particularly we are interested in sublinear with respect to this size parameter m. So the m of x, so that's the size associated with the input x, right? This value to the epsilon. Epsilon is a constant, smaller than 1. Right? Do you remember the directed graph situation here? There, right? It's a polylog in the size of x. So this is a standard size. Okay. So in the following slides, I just keep using the sublinear space. That means this one. Okay. Well, sometimes people use n to the 1 minus 1 over x n or something. Right? So that is smaller than, strictly smaller than n, so that is sublinear. But I'm using a very strong sense. Actually, n to the epsilon is smaller than 1, constant. Okay. So now we are actually going to focus on sublinear space computability. Okay. I'll introduce the complexity class, the parameterized p-time space, f of n. Well, we are sticking to the polynomial time, so I don't need to specify the time bound. But the space, well, the f is the space bound. If x is in L, then m accepts x. X is not in L, m reject x. But the polynomial time running time, but the space usage has to be restricted to the O of f of m of x. So because it's parameterized. Okay, so now we are looking at the two-sat case, right? A two-sat means the standard, the 2CNF formula with n variable and m clauses. So this, well, the best possible algorithm shows the space bound here, n to the 1 minus c over square root log n. So you are familiar with this number, right? So this is actually taken from the graph or the bounds algorithm. Okay. So you see the now we want to make it m to the epsilon, right? So we don't know whether this is true or not, but this is the currently known best possible bound. So we just make it slightly smaller than this. You see how close they are, right? Okay. Now we want to do the complexity class. P sublime. The P stands for the polynomial time. Sublime stands for sublinear space. Okay. So this is actually the parameterized problems, L comma M, and that is solved in polynomial time using sublinear space with respect to this size parameter. More schematically here. So this is the that's actually sit between the parameterized L, log space, parameterized polynomial time. But we don't know whether they are actually separated or plus. Okay. So now the reductions. So P sublime is a kind of funny complexity class. If you think about it in a standard reduction, well, so I'm going to use an Oracle Turing reduction using Oracle. Well, this one here, right? This is actually exactly the same as I showed before. We have a query tape, and the information is sent to the Oracle. Oracle actually changes the internal state direction, depending on the yes or no. Okay. So I introduced the one particular possible reduction. So it's called sublinear space reduction family. So we have for any epsilon actually comes in here. Right? We have an Oracle Turing machine, and we have some polylog function and some constant, and that satisfies the three clauses here. This m runs in polynomial time, and using this space. So this is sublinear space. So L is the polylog function, right? So this to the constant epsilon. Epsilon is smaller than 1, right? And M make an adaptive query to Oracle, right? And the size of the query satisfies the following condition. X is the original input, and Z is the query word. the size of the query word with respect to the size parameter M2 that belong to here, right, is bounded, upper bounded by size of x to the k1 plus k2. That means the polynomial in size of x. The size of x is the m1 of x, right, here. Right. So this is the actually the things. Now, in the standard polynomial time arc reduction, well, then this condition always holds, right? The size of query word is the bounded by the size polynomial in size of x, right? It's pretty much standard. Okay, right? Here is the point. The query word has size polynomial in the size of input. Okay. The problem is that p sub lin may not be closed under this reduction, or even there's a much weaker many one reduction using a log space. Even the log space reduction, this complexity class is not closed. So we have to really look into the different kind of the reduction. That is short reduction. What is short? Because the problem happens when you make a long query word, you have to make it shorter. So you only make short queries to the audience. Okay, now I just slightly change it. The original definition of the 1, 2 are pretty much the same, but the last one here, that is the linear in terms of the size of x. Previously, okay, I just skim it. Previously we had the polynomial in the size of x, but now it's the linear in the size of x. So that's the difference. So this is a short reduction. This is standard reduction. Then what happens? So the original one and the short version, they are the reflexive and transitive, but the p sub lin is closed under these short reductions. And the two concepts, the standard reduction and the short reduction, they are completely different. So because then we can actually find a recursive set that separate two notions. So we can construct it in a recursive way. Right? The interesting thing about this short reduction is that, well, using this short reduction, the 3 bars, I forgot to mention. The 3 bar means A is reducible to B, and also B is reducible to A. So that means an equivalent. Okay, 2 sub K is equivalent to 2 sub 3. So the K doesn't matter, right? So we don't need to think about it as a different K individually. And everything is go down to 3. So it's better to just think about it 2 sub 3 in the following slides. Right? And also important thing is that 2 sub 3 case, well, even if the K case, right? The size parameter, the different size parameter, in this case, the number of the variable, this is the number of the clauses, the complexity is exactly the same based on this reduction, right? That's the, do you remember the square difference, right? That disappeared here because we actually have a right definition of the reduction, right? The choice of the reduction is very important. If you just change it a little bit, then that's actually make a huge difference. So this is just one example. Right? So now we have to only consider this one, then 2 sub 3 and the number of the variables. So what is the complexity of this one, right? That this belongs to P sub lin, so that's a big question. Right? The problem is that we can't get rid of this subscript 3. Now, well, for the DSD content, we have the same situation. I didn't really write it down, but say D sub lin, sorry, the DSD con and sorry, the K DSD con and 3 DSD con. both are exactly the same complexity. Okay. So this is actually the overview of the complexity kind of relations, well, reductions actually. For example, the 3 DSD cone and the 2SAT3, they have the same complexity because according to the short reduction. We have a search version here, DSD cone here, right? So this is inside the P subdomain, and those are well, this is just the dotted line, so it's not the straight line. Maybe that contains the more complexity classes. I don't know, right? Search unique cycle, directed graphing cycle, and also there's lots of interesting things here, right? So here is the breadth first and search problem, right? And so on. Okay, so we are actually getting into the core of the topic here. So instead of this one, we actually take this one here, right? But we don't know whether the 2SAT or even the 2SAT3 requires this space. We know they are solved in this space, but not known using this space, right? So it might be possible to to give the assumption or hypothesis that says this may not be computable using this amount of space, right? This might be the best possible result, right? Natural somehow, it's just a working hypothesis. So the hypothesis called the linear space hypothesis, well, the name comes from the exponential time hypothesis. You can see that. Just the linear space version. Okay, so this hypothesis said that there is no deterministic algorithm that solves the 2SAT3 using polynomial time, using this sublinear space in terms of the number of the variables. Well, you can change it to number of the clauses if you like. It doesn't matter, right? And the epsilon, the important thing is the epsilon is a constant. Okay. So, as I said, we don't know whether we can actually drop this 3. Okay, sure. Go ahead.
Oh,
Question?
no, I just want to take 5 minutes.
Oh, I see. Okay. All right. So, as I said, we have the equivalence between those problems. So we can actually replace the number of variable by number of the clauses. Right? And the interesting thing about this one is, if this assumption or hypothesis is true, then NL is different from L. Because, well, basically, 2SAT3 cannot be solved in sublinear space. That means even the log space is impossible. Right? So that means the NL is different from L. Right? So the assumption is slightly stronger than this assumption. And we have more, the problems that is equivalent to the linear space hypothesis. For example, a linear programming problem. So this is the instance is the n by n matrix and rational column vector. And the important thing here, the restriction here. Each row of A has at most 2 non-zero entries. Very sparsely, the number is distributed. Most of the parts are zeros. And each column of A has at most k. Well, k is that comes from here, right? Non-zero entries. And we will use the size parameter, something like the number of the columns or numbers of rows. And this is actually NL complete. It's not so difficult. Well, this is the situation here. So we have a matrix A and the vector here, and the column vector here. Then we try to solve the question here. So the question is whether we have a solution or not. Okay. So this problem is also is equivalent. So we can actually swap the 2SAT3 with LP 2,3. So So this is the last part here, the application, right? We have a hypothesis, but how can you use it, right? So that's the most important thing. So now we start with an NL, non-deterministic log space search problem. So this is just one of the search problems here. The search UOCK. So this is the variant of the knapsack problem. We have a W here. So this is the input string. And also we have a sequence of segmented strings. Okay? And now the assumption is WI is a substring of W. So that has to be some part of the W. And this one is unique. So we can't find the same strings in any other place. So you can uniquely spot it. Right? So that's the assumption. Now the solution is the sequence here. For example, if this is W and this is the series of the strings, right? So you can actually pick W1 here and the W3 here and the W5. Then we can actually form exactly the same input string. So the answer is 1, 3, 5. So this is the answer. It's simple, right? So you can, you are asked to find those series. It's simply very simple in the, from the polynomial type point of view. But in the log space, or much smaller space, right? The linear space or much smaller space. Okay. So this is the game, right? The size parameter is the number of the elements, n. So that appeared here, right? So that's the parameter. So how many WIs? Okay. So if linear space hypothesis is true, then for any epsilon, right, there is no polynomial time n to the a half minus epsilon, 1/2 minus epsilon space algorithm. Right? So we have the bounds on the space usage for solving this problem. Assuming that the linear space hypothesis is true. Right? Well, I don't know how you evaluate this result. It's nice to me. Okay, another one. Well, this is the optimization problem. Okay, so the optimization problem is similar to the search problem, but we have to try to find an optimal solution, or close to the optimal solution. Right? The how close is actually defined by the cost functions, and NLO is the NL optimization problem, the class of NL optimization problem. O stands for the optimization, and that is defined by Tanaka some time ago. And LSAS is the class of NL optimization problem that has log space approximation scheme. Okay, approximation scheme means a log space approximation scheme is we have a deterministic algorithm that takes x comma k is the parameter, right? And then try to find the solution y, okay, using this space, f of k times log n size of x, with the performance ratio is 1 plus 1 over k. Performance ratio is the fraction here. This m star is the optimal solution, right? This is actually the solution outputted by the machine, right? So the ratio here. Okay. So this is actually slightly worse, right? 1 plus 1 over k. The k is the parameter given by as the input. So if you take a bigger k, so this value close to 1. If this is 1, that means you are finding the exact optimal solution. Right? All right. So the Tanto introduced the maximum hot potato problem. The n by n matrix, right? The entries are numbers up to between 1 and n at the integer, and number d and starting index I, right? And the solution is the series of indices. And then you can take so this is the matrix, right? and I sub j comma I sub j plus 1. So you have a matrix. You actually pick here and pick here, and then if this is I, this is j, now it's the j and k and so on. Right? So you just simply play around this matrix, and then you simply sum them up. And the parameter is the number n here. Right? So this problem can be solved, it can be solved in LSAS. That means a log space approximation scheme. Right? But it is hard for LO and approximation preserving exact NC1 reduction. So if you take a weaker reduction, then it is very hard, even for an LO. So if the hypothesis, the linear space hypothesis is true, then for any epsilon, well, there is no polynomial time, k to the 1/3 times log the size of x space finding 1 plus 1/k approximate solution. So this is actually space bound, the lower bound. Okay, so this is the last example. Okay, sorry, yes, this is just last one. The topological sorting problem. So we have an acyclic directed graph like this one, and we have a starting point here. So topological sorting is that the all arrows goes in one direction, right? You have to sort them out. Now, so this is the result. If the linear space hypothesis is true, then there is no deterministic algorithm solving this problem in polynomial time using the number of vertices to the 2 to the epsilon space for any fixed constant. Okay, so there's a bunch of them open questions. Well, okay, thank you very much, and I'm happy to take it.
Are there any questions? So the goal, I mean, it's like you're trying to do fine-grained complexity, I guess, based on linear space
Yeah, that's right,
hypothesis.
that's right.
So it's very much in following the approach of the exponential.
Time high, yeah, hypothesis.
Very interesting. Okay.
Well, thank you.